Picture a catastrophic power failure in a server farm. The lights go dark, alarms trigger, and two opposing security protocols activate simultaneously. Physical security systems operate under a primary directive to protect human life. During a fire or a power loss, every physical and electronic barrier in the building must fail open to guarantee an unobstructed evacuation route. Logical security systems operate under a mandate to protect data confidentiality. When a network detects an anomaly or loses connectivity, the system defaults to a fail-closed state, locking down access to prevent unauthorized breaches. The physical domain prioritizes egress by failing open, while the logical domain mandates protection by failing closed. In modern networks, these two sides converge into a single risk profile. Architects must satisfy both opposing defaults simultaneously. Treating physical facilities and logical access as isolated disciplines creates systemic vulnerabilities. If these layers do not sync during a crisis, a fail-closed network could trap occupants in a burning building, or a fail-open door could expose the physical hardware of the data center. Emergency egress relies on the mechanical distinction between fail-safe and fail-secure hardware. Fail-safe locks require electrical power to stay locked, whereas fail-secure hardware requires power to unlock. The NFPA 101 Life Safety Code mandates a continuous, unobstructed path of travel from any occupied point in a facility to a public way. Occupants must be able to exit without credentials, keys, or specialized knowledge. This matrix contrasts the two primary locking hardware classes against fire code constraints. The choice of hardware determines whether a secure room defaults to an open or closed state during a power loss. Electromagnetic locks, or maglocks, are inherently fail-safe because they have no moving parts. If power drops, the magnet de-energizes and releases the door. To comply with safety codes, they also require manual auxiliary push buttons and motion sensors that cut the circuit when an occupant approaches. Fire-rated door assemblies require fail-secure electric strikes to maintain positive latching, which prevents draft pressures from pushing doors open and spreading smoke. For egress, these doors use a mechanical handle on the inside that physically retracts the latch bolt, overriding the electronic lock. These mechanical bypasses must meet ADA accessibility metrics. Interior doors with electronic access control require an activation force at or below 5 pounds, ensuring occupants with physical limitations can operate the hardware. Even purely mechanical hardware often relies on digital commands. Automated turnstiles and electronic locks require continuous communication with localized programmable logic controllers to process credentials.
Faster, more urgent tone. If a database server goes offline or network connectivity freezes during a fire, a logically closed system could trap occupants. Safety codes require these controllers to be programmed to drop all physical barriers immediately upon losing a network signal. The physical survival of occupants depends on localized software code successfully failing open the moment it is instructed to do so. Logic-based emergencies occur when primary authentication systems fail, such as a multi-factor authentication outage or a collapse of the federated directory service. Organizations regain control through break-glass architectures. These are highly privileged, temporary accounts engineered to bypass standard conditional access and privileged identity management workflows. This flowchart illustrates how different identity environments isolate these emergency credentials to ensure they remain accessible when primary authentication is unavailable.
In Microsoft Entra ID, cloud-only global administrators are secured with physical FIDO2 hardware keys. These accounts are placed within restricted management administrative units to prevent unauthorized credential modifications by other admins. Google Cloud stores its emergency credentials within an isolated project using Secret Manager. On-premises Active Directory environments utilize Tier 0 accounts, restricted by group policy, which ensures they can only execute on domain controllers and blocks logins from standard workstations. Because these accounts bypass enterprise guardrails, their activation triggers an immediate zero-threshold alarm. SIEM platforms flag even a single login attempt by a break-glass identifier. Once the emergency is resolved, the workflow requires automated scripts to revoke all active sessions and execute a mandatory rotation of the credentials. Engineering a logical fail-open bypass requires creating the most strictly monitored and heavily isolated boundary in the enterprise. Security teams also execute proactive threat hunting to stop advanced persistent threats that have bypassed automated defenses. David Bianco's Pyramid of Pain ranks threat indicators based on the operational cost inflicted on an adversary when those indicators are blocked. Blocking low-level indicators at the base of the pyramid provides limited security value. Attackers can easily recompile malware to change a hash or rotate IP addresses through proxies and VPNs. Hypothesis-driven threat hunting prioritizes TTPs, the tactics, techniques, and procedures of the attacker. Forcing an adversary to change their fundamental methodology requires an expensive and time-consuming operational retooling. When AI security agents detect behavioral anomalies at the TTP level, the system automatically triggers data loss prevention gateways to fail-close the network boundaries. This graphic shows how converged data loss prevention operates across 3 distinct data states to enforce those boundaries. Network DLP inspects data in motion. It uses TLS decryption to scan outbound traffic, blocking unauthorized exfiltration attempts across emails and web proxies. Endpoint DLP secures data in use. It monitors client devices to halt local actions, such as copying proprietary files to a USB drive or utilizing the clipboard for unauthorized transfers. Cloud DLP secures data at rest. It uses API integrations to scan storage buckets and automatically revokes public sharing permissions or exposed links. Hunting at the apex of the behavioral pyramid allows an enterprise to identify threats early enough to trigger a fail-secure state across its data transit and storage environments. Physical and logical domains share a recursive dependency loop. A logical break glass credential must be secured inside a physical fireproof safe. Conversely, physical egress relies on a logical pulse. An electronic door releases only when a controller drops the current. A breach of physical security exposes the logical domain to compromise, while a failure in logical systems during a fire prevents emergency egress. The technical outcome of one failure determines the failure of the other. To manage this dependency, organizations must integrate physical badging logs and logical directory authentications into a central SIEM. Correlating these telemetry streams allows security teams to detect impossible travel anomalies, such as an identity authenticating a logical session in one city while their physical badge is being used in another. Enterprise resilience is achieved when physical safety, logical access, and threat intelligence are engineered to exchange telemetry and synchronize their fail states.
An enterprise data center registers a critical alert. A 0-day vulnerability has been identified on a live production server. The immediate instinct of any engineering team is to quickly write and deploy a patch. But injecting unvetted code into a live production baseline routinely triggers system instability, resulting in catastrophic operational downtime that can cost more than the initial exploit. Resolving this operational paradox requires integrating vulnerability management into a broader governance structure that accounts for both software security and system stability. Organizational resiliency requires the enterprise defense triad. Layer 1, vulnerability mitigation, provides logical software defense. Layer 2, baseline change control, forms a safety net to deploy fixes without downtime. Layer 3, physical protections, supplies hardware security to stop adversaries from bypassing logical perimeters. These 3 domains are interdependent. A physical security gap can invalidate the logical layers, making it impossible to satisfy the rigid audit requirements of frameworks like NIST and PCI-DSS. Patch management operates as a heavily governed pipeline designed to strictly isolate unvetted code from live production data. How fast a patch must move through this pipeline is not left to developer discretion. Regulatory compliance frameworks dictate strict service level agreements, or SLAs, that establish maximum remediation timelines. Organizations determine these timelines by cross-referencing the common vulnerability scoring system against threat intelligence feeds like the CISA Known Exploited Vulnerabilities Catalog. The resulting mandates are absolute. A critical vulnerability demands full remediation within 72 hours, whereas standard preventative maintenance on low-risk systems allows up to 150 days. Compliance auditors do not ask for estimates on these timelines. They require mathematical verification using a metric called the mean time to remediate, or MTTR. This formula calculates the exact MTTR of an environment. We take the timestamp of the verified patch application,
and subtract the timestamp of the initial vulnerability identification. We then divide that sum by the total volume of remediated vulnerabilities within the audited timeframe. To pass an audit, organizations must leverage this math to prove a 95% critical patch compliance rate across all in-scope endpoints and network devices. Yet, highly sensitive environments enforce an ultimate constraint on this pipeline, such as the strict IRS guidelines for handling federal tax information, or FTI. No matter how urgent the MTTR requirements dictate a patch must be applied, security testing is legally prohibited from occurring on any system that utilizes active FTI. Engineers are required to build staging environments utilizing sanitized mock data. This prevents accidental exposure of citizen data during the quality assurance process. While MTTR measures the speed of security, forcing patches into live environments without rigorous staging introduces unacceptable risks to data integrity. Resolving this tension requires the second layer of the triad. Baseline change control operates as a mandatory second pair of eyes. Its function is to guarantee that an aggressive security patch doesn't accidentally execute a self-inflicted denial of service attack. Every system modification follows a strict cyclical lifecycle, moving from risk assessment and staging through implementation and concluding with a post-deployment review. The gatekeeper of this lifecycle is the Change Advisory Board. This cross-functional group weighs the security risk of remaining unpatched against the operational risk of breaking a live production baseline. To prevent this board from becoming an organizational bottleneck, routine, standard changes utilize pre-approved automation templates to bypass direct review, reserving the board's deep technical scrutiny for major, high-impact modifications. The overall health of this deployment lifecycle is tracked using an active metric called the change success rate. We divide successful, incident-free deployments by total executed changes. Stable IT environments maintain a change success rate between 85 and 95%. In fragile architectures, that degrades to 60 or 70%, proving a high cost of ownership and signaling an urgent need for modernization. Because deployments will inevitably fail, compliance frameworks mandate that every non-standard change includes a meticulously documented rollback plan. The most critical threshold defined within that plan is the point of no return. The point of no return is the exact operational boundary during a deployment, where reverting to the old baseline would cause unacceptable data corruption. Once crossed, engineers must abandon the rollback strategy and execute an emergency forward fix. A 95% change success rate and a perfectly calculated point of no return secure the logical pipeline, but they offer zero defense if an adversary bypasses the network entirely and attacks the hardware directly. The primary blind spot in logical engineering is the assumption that network segmentation and automated patching provide complete isolation. If an attacker accesses a legacy point-of-sale terminal, they can plug in a USB device and bypass the logical firewalls completely. For end-of-life systems where software updates are no longer possible, rigid physical protections act as the ultimate compensating control. Securing these boundaries requires the exact correlation of physical and logical logs. A keycard swipe at a server room door must immediately register within the Centralized Security Information and Event Management System. Managing physical access introduces direct friction between security compliance and privacy legislation. Storing visitor data indefinitely satisfies security audits, but violates GDPR storage limitation principles. Automated visitor management systems resolve this conflict. They enforce corporate legal holds when necessary, while automatically purging standard visitor data after a strict 90-day window to maintain privacy compliance. The final operational requirement for physical security is continuous visual auditing. Frameworks like PCI-DSS mandate unbroken camera coverage over all sensitive entry points. Maintaining a mandatory 90-day retention floor for enterprise video surveillance requires specific deterministic storage math to avoid overwriting crucial evidence. Calculating that exact hardware requirement relies on this formula. Total storage capacity is the product of active cameras multiplied by their average bitrate, daily recording hours, and the required 90-day retention period. This combination of physical entry management, data retention, and storage math forms the final defensive layer of the enterprise triad. When the patch pipelines, the change advisory board gateways, and the physical camera perimeters operate simultaneously, the governance model is complete. To make this system auditable, These three distinct layers share a single technical thread: authoritative network time protocol, or NTP, synchronization. If a surveillance camera's internal clock drifts even a few minutes from the logical firewall logs, forensic analysts cannot correlate physical entry with digital access. The audit trail is broken, and compliance fails. The final human element enforcing this structure is strict role-based separation of duties. Software developers writing the patches must be cryptographically prevented from accessing the physical scripts used to deploy them. This rigorously governed infrastructure is currently facing its ultimate test, an advanced cryptographic threat known as Harvest Now, Decrypt Later. Adversaries are actively intercepting and storing highly sensitive encrypted network traffic today. They are waiting for the exact moment when quantum computers possess the processing power to break current cryptographic baselines. Surviving this quantum shift will force organizations to rely on the exact triad they've built. They will need structured board approvals, isolated staging environments, and verified rollback plans to safely strip out and replace core cryptographic algorithms without breaking the enterprise. By maintaining these three layers, organizations transform governance into a synchronized, mathematically verified defense of the production baseline.
Welcome to this explainer. Today, we're doing something really cool. We're decoding the incredibly complex world of enterprise security by actually visualizing your organization as a modern fortress. We're going to build this thing from the ground up. We'll design the vaults to protect your most valuable assets, engineer the gates, and deploy the guards. By the end of this, you're going to see exactly how the world's most secure networks actively defend against relentless modern adversaries. So here's our blueprint for today. We'll start deep inside at the data vault, then move out to see how the fortress handles system failure states. After that, we'll inspect the guards patrolling our perimeter, and finally look at breaking the glass, our emergency access protocols. Let's get into it. Section 1. Protecting the data vault. This is all about securing the core. Okay, to protect our deepest vault, we absolutely have to secure sensitive information across 3 different states: data in use on endpoints, data in motion across your networks, and data at rest in databases. Securing all 3 of these is what ensures compliance with rigorous frameworks like NIST Special Publication 853. To actually enforce these boundaries, organizations use data loss prevention, or DLP. Think of DLP as the automated guards checking literally every single item that tries to leave the vault. It monitors, logs, and actively blocks unauthorized transfers. But, here's the catch. Traditional DLP guards using simple rulebooks, they can actually be pretty clumsy. And it turns out there is a massive difference between old-school security and modern precision. See, traditional pattern matching just looks for general formats, like, say, any 16-digit credit card number. But what happens if an employee just buys a coffee online during their break, or an accountant runs a totally standard corporate payment? Boom, the system sounds the alarm, and that creates massive alert fatigue. Modern Exact Data Match, or EDM, completely solves this. It takes your highly structured, proprietary database records, scrambles them into precise cryptographic hashes, and only triggers an alert if those exact corporate hashes try to leave the network. Benign personal data, it just passes right on through. But wait, what if an employee is disconnected from the cloud? Like, say they're working offline on a long flight. Well, that's exactly where Endpoint Match Data Identifier, or EMDI, comes into play. Cloud-based EDM is, pretty heavy. It requires a constant server connection. EMDI, on the other hand, executes locally, right on the endpoint itself. It uses a fraction, just 1/5 of the memory footprint of cloud EDM. And crucially, because it's local, it can take synchronous actions. It can instantly block a file transfer or encrypt a document in real time, even if that laptop is sitting in airplane mode. Of course, not all data lives neatly in a little database spreadsheet, right? Beyond databases, we have to secure unstructured assets. We're talking proprietary CAD files, source code, legal templates. We do this using index document matching, or IDM, which basically creates a unique fingerprint of the entire file. But to truly stop threats, we can't just look at the files themselves. We have to look at behavior. We tie these DLP alerts into managed detection and response platforms, like Terramind, for example, which monitor behavioral anomalies. Think strange clipboard interactions or unusual app usage. This catches malicious human intent way before your proprietary data just walks out the door. Section 2. System failure states. Let's talk about navigating crises. All right, let's move out to the fortress gates. Have you ever wondered what happens when the systems powering our defenses suddenly crash, lose power, or come under attack? It's a completely critical question every security architect has to face. When the power suddenly drops, do we prioritize human life and let everyone out? Or do we prioritize our assets and lock everything down tight? So the crucial point here is balancing safety and security. In physical building design, a fail-safe lock, like an electromagnetic maglock, requires power to stay locked. If the power drops, the door automatically unlocks. This is absolutely essential for life safety, allowing for rapid evacuation. But a fail-secure lock, like a heavy-duty mechanical strike, stays locked from the outside when the power dies. Actually, under fire codes like NFPA 80, fire doors must be fail-secure. They have to stay latched to contain deadly smoke while still allowing people on the inside to manually push their way out. Now, this logically extends directly into our software systems. Just as physical doors fail open for life safety, some network systems prioritize availability. For example, Cisco Umbrella can be configured to fail open, letting DNS traffic keep flowing out to the internet even if the security checkers totally crash. But for your deepest secrets, you absolutely must fail closed. High-security authorization engines like CISSP default to deny. If the database crashes, nobody gets in. And guess what? Attackers know this. They will actively try to crash your systems, basically crossing their fingers that you incorrectly configured a fail-open state. Section 3. The guards. Time for some proactive defense. Because simply setting up automated locks and waiting for them to ring just isn't enough anymore. We have to look at the active defenders. The whole paradigm has completely changed. Under mandates like NIST SP 800-53, organizations are actively shifting away from reactive firewalls that just passively ingest static lists of bad IP addresses. Instead, they're moving to active, human-led threat hunting. And these threat hunters operate on a pretty terrifying but necessary assumption. The automated alarms missed something, and the attacker is already inside the network. Let's build David Bianco's famous pyramid of pain to see how this proactive hunting actually hurts the attacker. Down at the bottom, blocking file hashes or IP addresses, that's trivial. An attacker can change an IP in seconds. But as we move up through domain names, network artifacts, and the attacker's custom tools, it gets significantly harder for them. Finally, at the summit, we have TTPs, tactics, techniques, and procedures. If our threat hunters can detect and disrupt an attacker's core behavioral methods, we inflict maximum pain, practically forcing them to completely reinvent how they operate. But here's the million-dollar question. How do you hunt for invisible behaviors without completely exhausting your human analysts? Well, modern security operations centers deploy AI-powered agents. These AI agents rapidly ingest threat intelligence, correlate thousands of hidden log connections, and then map them directly to the MITRE ATTK framework. They build a hypothesis and hand a fully contextualized alert right to a human analyst. This is an absolute game changer because it saves your human analyst from total burnout, letting them make the strategic, big-picture calls while the AI handles all the grueling data lifting. Section 4. Breaking the glass. Emergency access. Okay, so what happens if our high-security identity systems go into absolute lockdown? The authentication servers crash, and they trap the rightful administrators outside during a major crisis. Well, we obviously need a way back in. But relying on static, pre-made emergency accounts, like admin123 or password 2024, is a massive security risk. It's quite literally the equivalent of building a billion-dollar digital fortress and then hiding the master key right under the front doormat. If an attacker finds that static break glass credential, they own your entire enterprise. The modern sledgehammer to safely break that glass is Privileged Access Management, or PAM. Instead of a static password, modern break glass protocols use asymmetric encryption to instantly generate dynamic, single-use credentials. And get this, these passwords self-destruct the exact second the administrator logs out. Furthermore, they're protected by strict anti-tampering clock protections, meaning an adversary can't just roll back the server time to sneakily extend their access window. Every single keystroke during this emergency session generates a real-time audit log, ensuring complete and absolute accountability. Building a modern security architecture really requires balancing data protection, system reliability, and proactive threat hunting. As we wrap up this explainer, I want to leave you with this final, provocative thought to take back to your own teams. Think about it. If your physical and digital doors failed right now under a targeted attack, would your enterprise fail open to disaster or fail secure to safety? Thanks for exploring the modern fortress with me today.